Hello there, and welcome. I'm so glad you're here. Maybe it's been a long day, or maybe you're the kind of person who likes falling asleep to cosmic mysteries instead of counting sheep. Either way, tonight's journey is for you. You don't need to do anything now but rest. Let your breath slow, your thoughts soften, and your body grow light as if gravity has loosened its grip. Because tonight, we're going to explore one of the solar system's strangest mysteries, a missing planet. Or rather, the place where a planet should have been, but never was. Between Mars and Jupiter, there's a gap, a vast empty region scattered with millions of rocks, some as small as pebbles, others as large as mountains. We call it the asteroid belt, and for centuries, scientists have wondered why there's no planet there. What happened in that space? Was there ever a world that shattered into pieces? Or did something prevent a planet from forming at all? By the end of this journey, you'll understand the mystery, the clues we've found, and the questions that still keep astronomers awake at night. And just before we begin, if these quiet explorations help you unwind or give you a peaceful way to end your day, consider gently tapping the like button and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now, let's begin. Let's start with something you can picture. Imagine the solar system laid out before you like a map. Close to the sun, you have the rocky inner planets. Mercury, small and scorched. Venus, wrapped in thick acidic clouds. Earth, our home, blue and green and alive. And Mars, the red desert world, cold and dusty and quiet. Then there's a gap, a wide empty space. And beyond that gap, you find Jupiter, the giant, a world so massive it could swallow over 1,000 Earths. It's enormous. It dominates the outer solar system with its gravity, its storms, its dozens of moons. The distance between Mars and Jupiter is huge. Mars orbits about 228 million kilometers from the Sun. Jupiter orbits about 778 million kilometers away. That's more than 3 times farther. There's a vast amount of space between them. And for a long time, people wondered, why is there such a large gap? Why doesn't something sit in that empty region? A planet, perhaps, to fill the void? In the late 1700s, astronomers noticed something curious. There seemed to be a pattern in the spacing of the planets, a mathematical relationship that predicted where planets should be found. It wasn't a law of physics exactly, more of an observed pattern, but it was striking. This pattern is called the Titius-Bode law, named after the 2 astronomers who popularized it. Here's how it worked. You start with a sequence of numbers, 0, 3, 6, 12, 24, and so on, each number doubling. Then you add 4 to each number and divide by 10. The results you get match, surprisingly well, the distances of the known planets from the Sun, measured in astronomical units. Mercury, Venus, Earth, Mars, they all fit. Jupiter and Saturn fit too. But the pattern predicted something else. It predicted a planet between Mars and Jupiter at about 2.8 astronomical units from the Sun. And there was nothing there. At least, nothing anyone had seen yet. Astronomers began to search. If the pattern was real, if there was supposed to be a planet in that gap, then maybe it was just too faint to see. Maybe it was small, or dark, or hidden somehow. On the first night of the 1800s, January 1st, 1801, an Italian astronomer named Giuseppe Piazzi was mapping stars when he noticed something unusual, a faint point of light that moved slightly from night to night. It wasn't a star. Stars are fixed, distant suns that don't shift position quickly. This object was moving, which meant it was close, orbiting the Sun like a planet. Piazzi had discovered something new. He named it Ceres, after the Roman goddess of agriculture and grain. And for a while, people thought Ceres was the missing planet. It was in the right place, exactly where the Titius-Bode law predicted. The gap was filled, mystery solved. But then something strange happened. Other astronomers began finding more objects in the same region. In 1802, another one appeared. They called it Pallas. Then, in 1804, Juno, In 1807, Vesta. Each one was in roughly the same orbital zone between Mars and Jupiter, and each one was small, far smaller than any known planet. Ceres itself, the largest of them, was only about 940 kilometers across. That's less than the width of Texas. Earth, by comparison, has a diameter of nearly 13,000 kilometers. These weren't planets in the way we understood planets. They were something else. Fragments. Pieces. The astronomer William Herschel, who had discovered Uranus years earlier, gave them a new name. Asteroids, meaning star-like, because through telescopes they appeared as tiny points of light, like distant stars, rather than disks like planets. As the decades passed, more and more asteroids were discovered. Dozens, then hundreds, then thousands. By the mid-1800s, it became clear that the region between Mars and Jupiter wasn't home to a single missing planet. It was home to countless small bodies, a belt of rocky debris orbiting the Sun in a wide band. Today, we know of over 1 million asteroids in this region, though most are quite small. The four largest, Ceres, Vesta, Pallas, and Hygeia, contain about half the total mass of the entire belt. Ceres alone accounts for about a third. The rest is scattered among hundreds of thousands of smaller rocks, some only a few meters across. Think about that for a moment. Instead of one planet, there are millions of fragments. Some are round, shaped by their own gravity. Others are irregular, jagged chunks of rock and metal tumbling through space. They orbit the Sun in a wide zone, roughly between 2.1 and 3.3 astronomical units, though some wander closer or farther. And here's what's strange. If you added up all the mass in the asteroid belt, all the rocks, all the dust, all the fragments, it would only amount to about 4% of the Moon's mass. That's tiny. The entire asteroid belt contains less material than a single small moon. So the question becomes, not where did all the material go, but why is there so little material there in the first place? Can you picture it? A region of space vast enough to hold a planet, but filled instead with scattered rubble. A cosmic construction site where something went wrong, where the building blocks were there, but they never came together. Or maybe they did come together briefly, and then broke apart. The mystery isn't just about what's missing, it's about what's left behind. And what those fragments can tell us about the early solar system, about how planets form, and about the forces that can prevent a world from being born. When you look at the asteroid belt through a telescope, you don't see a dense cloud of rocks. You see mostly empty space. The asteroids are spread so far apart that spacecraft can pass through the belt without much risk of collision. The images we often see in movies of ships dodging through fields of tumbling boulders aren't accurate. The reality is quieter. The asteroids drift in their orbits, separated by millions of kilometers, moving in silence through the dark. But even though they're far apart, their existence raises questions. Questions that scientists are still working to answer. Here's the thing most people don't realize. The asteroid belt might be the key to understanding not just what happened between Mars and Jupiter, but how the entire solar system formed. These fragments are ancient. They're leftover material from the very beginning, from the time when the Sun was young and the planets were still taking shape. Some asteroids are made of rock. Others are rich in metal, iron, and nickel, the same materials found in Earth's core. Still others are dark and carbon-rich, covered in organic compounds that might have been the building blocks of life. Each type tells a story about temperature, pressure, distance from the Sun, and the chaotic dance of gravity that shaped the solar system over millions of years. And so we're left with the question that will carry us through this journey. Why is there no planet between Mars and Jupiter? Was there ever a planet that broke apart, scattering into millions of pieces? Or did the asteroids never come together at all, held apart by some invisible force? The answer, as we'll discover, involves Jupiter's enormous gravity, the timing of the solar system's formation, and the delicate balance between creation and destruction. It's a story written in stone, floating silently in the space between worlds. A story we're only beginning to read. As you drift towards sleep tonight, hold that image gently in your mind. A belt of ancient rocks drifting in the dark, each one a fragment of what might have been, each one carrying secrets from the earliest days of our cosmic neighborhood. And as we continue this journey together, we'll uncover those secrets, one quiet piece at a time. Before we move on, I'm curious. If you had to guess right now, do you think there was once a planet that shattered? Or do you think the planet never formed at all? It's a question worth wondering about as you rest. For now, the asteroids keep orbiting, patient and silent, waiting for us to understand their story. And in a moment, we'll explore what scientists first believed happened in that empty space, a theory that seemed to explain everything until the evidence proved otherwise. For over a century, the most popular explanation for the asteroid belt seemed obvious. There must have been a planet there once, a world that formed like the others, that orbited between Mars and Jupiter for millions of years. And then, something catastrophic happened. A collision, perhaps, or some violent event that shattered the planet into countless pieces, scattering them across the space where it once existed. The asteroid belt, in this view, was a graveyard, the remains of a destroyed world. It's a compelling idea, and honestly, it makes sense at first glance. If you see millions of rocks orbiting in a region where a planet should be, the natural assumption is that those rocks came from somewhere, that they were once part of something larger, that they're fragments of a whole that no longer exists. Scientists in the 1800s called this hypothetical planet Phaeton, named after the Greek myth of a chariot driver who lost control and was struck down by Zeus. A fitting name for a world that supposedly met a violent end. The theory gained traction for several reasons. First, the asteroids are spread across a zone that fits the spacing pattern of the other planets. Second, some of the asteroids have compositions that suggest they came from the interior of a larger body. Metallic asteroids, for instance, are rich in iron and nickel, similar to the core of a planet. If a planet had been torn apart, you'd expect to find fragments of its core, mantle, and crust scattered through space. And that's what some people thought they were seeing. But here's where the theory starts to fall apart. When scientists began to study the asteroids more closely, when they measured their sizes, their masses, their compositions, the pieces didn't fit together the way they should. The first problem is mass. Remember what I mentioned earlier? If you took every asteroid in the belt, every rock, every grain of dust, and combined them into a single object, the result would have only about 4% of the moon's mass. That's not a planet. That's not even close to a planet. Think about that for a moment. The moon, Earth's quiet companion, is considered small by planetary standards. It's about a quarter the size of Earth. And yet, if you gathered every single fragment from the asteroid belt, you'd end up with something much smaller than even the moon. A tiny world, barely large enough to hold itself together. So, if the asteroid belt is the remains of a shattered planet, where did all the rest of the mass go? Did it escape the solar system entirely? Was it pulled into the sun? Or absorbed by Jupiter? None of these explanations work well. There's simply not enough material in the asteroid belt to account for a full-sized planet. The second problem is composition. When you look closely at the asteroids, they're not all the same. Some are rocky, made of silicate minerals like the surfaces of Earth and Mars. Some are metallic, dense chunks of iron and nickel. Others are carbonaceous, dark, and rich in organic compounds and water ice. These differences suggest the asteroids formed in different regions, at different temperatures, under different conditions. If they all came from a single shattered planet, you'd expect them to have similar compositions, layered perhaps, with core material in one place and crust material in another. But that's not what we see. The asteroids are too diverse. They don't look like fragments of one world. They look like pieces that were never part of the same body to begin with. And then there's the spacing. If a planet exploded, you'd expect the fragments to be clustered relatively close together, at least at first. Over time, their orbits might spread out, but there should still be some concentration, some sign that they originated from a single point. Instead, The asteroids are scattered across a huge region, with gaps and clusters that don't match the pattern you'd expect from a catastrophic breakup. Some asteroids orbit closer to Mars, others drift near Jupiter. The distribution is uneven, chaotic, shaped more by gravitational resonances than by a single violent event. Can you picture it? Instead of a neat explosion, with debris radiating outward from a central point, the asteroid belt looks more like a cloud that was never gathered in the first place, like dust that drifted through space but never coalesced, like building blocks that were laid out but never assembled. The evidence kept pointing away from the shattered planet theory. And as technology improved, as telescopes became more powerful and spacecraft visited the asteroids up close, the theory became harder and harder to support. In the 1970s and 1980s, computer simulations allowed scientists to model what would happen if a planet between Mars and Jupiter actually broke apart. They could simulate the gravitational effects, the collisions, the way debris would spread over time. And what they found was striking. Even in the simulations, the fragments didn't behave the way the asteroid belt behaves. A shattered planet would create a debris field that looked different, tighter, more uniform. The asteroids, instead, seemed to follow patterns shaped by Jupiter's gravity, by resonances and perturbations that prevented them from ever coming together. One by one, the pieces of the shattered planet theory fell away. It was a beautiful idea, dramatic and tragic, the story of a world that once was and is no more. But the universe doesn't always give us the stories we expect. Sometimes the truth is quieter, stranger, more subtle. And in the case of the asteroid belt, the truth pointed toward something different. Not destruction, but prevention. Not a planet that died, but a planet that never lived. By the late 20th century, most astronomers had abandoned the idea of Phaeton. The evidence simply didn't support it. The mass was too low, the compositions were too varied, the distribution was wrong, and yet the question remained. If the asteroids aren't the remains of a destroyed planet, then what are they? And why is there no planet between Mars and Jupiter? The answer, as we'll see, has everything to do with Jupiter itself. With its enormous size, its powerful gravity, and the way it shaped the early solar system like a sculptor working with clay, pulling and pushing the material around it, preventing a world from ever forming in the space just inward from its orbit. But before we get to Jupiter's role, there's something else worth considering. Even though the shattered planet theory is no longer accepted, collisions still happen in the asteroid belt. Asteroids do smash into each other. They break apart. They create smaller fragments. We've seen evidence of this. Some asteroids are clearly pieces of larger bodies that were broken by impacts. We call these families groups of asteroids that share similar orbits and compositions, suggesting they came from a common parent body. One of the most famous is the Vesta family. Vesta is one of the largest asteroids, about 525 kilometers across, with a surface marked by a massive crater near its south pole. That crater was created by a colossal impact, one so powerful it blasted fragments into space. Some of those fragments still orbit nearby, smaller asteroids that can be traced back to Vesta through their chemical signatures. So yes, asteroids can shatter, worlds can break apart. But the asteroid belt as a whole isn't the result of one such event. It's the result of something else entirely. As you rest tonight, let that sink in gently. The idea that seemed so obvious, so natural, turned out to be wrong. The asteroid belt isn't a cemetery. It's not the grave of a lost world. It's something more subtle, a place where a planet tried to form, where the ingredients were present, but where something interfered. Something stopped the process before it could complete. And that something, as we'll explore next, was waiting just beyond the belt, massive and patient, pulling at the scattered rocks with invisible threads of gravity. Here's a thought to carry with you. Sometimes what's missing tells us more than what's there. The absence of a planet between Mars and Jupiter isn't just an empty space. It's a clue, a signpost pointing toward the forces that shaped our solar system in its earliest days. Forces that are still at work, even now, billions of years later. If you were an astronomer in the 1800s, looking at the asteroid belt for the first time, would you have believed in the shattered planet? Or would you have suspected something else was going on? It's easy to see patterns where we want to see them, to tell stories that make sense of the chaos. But the universe asks us to look deeper, to question, to let the evidence guide us, even when it leads somewhere unexpected. Now we come to the heart of the mystery. If the asteroid belt isn't the remains of a destroyed planet, then what stopped a planet from forming there in the first place? The answer lies just beyond the belt, in the massive presence of Jupiter, the giant, the largest planet in our solar system, a world so enormous that it contains more than twice the mass of all the other planets combined. Jupiter didn't just form alongside the other planets. It shaped them. It influenced them. And in the space between Mars and its own orbit, Jupiter's gravity prevented a world from ever being born. To understand how this happened, we need to go back to the beginning, back to a time over 4.5 billion years ago, when the solar system was young. There was no sun yet, not as we know it. No planets, no moons. Just a vast cloud of gas and dust, slowly rotating in space. This cloud, called the solar nebula, was made mostly of hydrogen and helium, the lightest elements left over from the Big Bang. But mixed into that gas were heavier elements, forged in the hearts of stars that had lived and died long before our sun was born. Carbon, oxygen, silicon, iron, the building blocks of rocky worlds. Something triggered the collapse of this cloud. Maybe a nearby supernova sent a shockwave through space. Maybe the cloud simply became dense enough that its own gravity pulled it inward. Either way, the center of the cloud began to heat up, growing denser and hotter as material fell toward it. This central region would eventually become the sun, but the rest of the cloud didn't fall straight in. It was rotating, spinning slowly through space, and as it collapsed, that rotation caused it to flatten into a disk, a protoplanetary disk swirling around the young sun like a cosmic whirlpool. In this disk, particles of dust began to stick together. At first, the process was gentle. Tiny grains collided and clung to each other through static electricity and weak forces. Dust became pebbles. Pebbles became boulders. Boulders became planetesimals, objects kilometers across, large enough that their own gravity started to matter. And once gravity took over, the process accelerated. Planetesimals attracted more material. They grew larger. They collided with each other, merging or shattering depending on the speed and angle of impact. Over millions of years, these collisions built the planets we know today. Close to the sun, where temperatures were high, only materials with high melting points could survive. Rock and metal. This is why the inner planets, Mercury, Venus, Earth, and Mars, are small and dense. They're made of the heavy stuff that didn't evaporate in the sun's heat. Farther out, beyond what we call the frost line, temperatures were low enough for water to freeze, and water ice is far more abundant than rock. This is why the outer planets, Jupiter, Saturn, Uranus, and Neptune, grew so large. They had access to a much larger reservoir of material. Jupiter formed first among the outer planets, and it formed fast. Within a few million years of the solar nebula's collapse, Jupiter had already gathered most of its mass. It became a giant, a world massive enough to hold on to hydrogen and helium, the lightest gases, the same materials that make up the sun. Jupiter is often called a failed star, though that's not quite accurate. It never came close to the temperatures needed for nuclear fusion. But it did become the second most massive object in the solar system, after the sun itself. And here's where the story of the asteroid belt begins to take shape. Jupiter's gravity didn't just affect Jupiter, it reached outward, pulling on everything nearby. The region just inside Jupiter's orbit, the space between Mars and Jupiter, felt this gravitational influence strongly. Planetesimals trying to form there were tugged and perturbed by Jupiter's presence. Their orbits became eccentric, elongated, tilted. Instead of moving in neat circles, they began to cross each other's paths. Think about what happens when orbits cross. Collisions become more violent. Instead of gentle mergers, where two planetesimals stick together and grow, you get high-speed impacts that shatter both objects into fragments. The material that should have been building a planet was instead being ground down, broken apart, scattered. Jupiter's gravity stirred the region like a spoon in a bowl of soup, preventing the ingredients from settling and solidifying. This process is called gravitational perturbation, and it's not unique to our solar system. Wherever you have a massive planet, it affects the orbits of smaller bodies nearby. But Jupiter's effect was particularly strong because it formed so quickly and grew so large. By the time the inner planets were still gathering material, Jupiter was already a giant, dominating the outer solar system with its gravity. Can you picture it? A region of space filled with rocks and dust, all trying to come together to build a planet the way Mars and Earth had done farther inward. But every time they started to gather, Jupiter's gravity pulled them apart. Orbits shifted. Velocities increased. Collisions became destructive rather than constructive. The planetesimals in that region never had a chance to grow. They were caught in a gravitational tug-of-war, unable to merge, unable to escape. Over time, many of these planetesimals were lost. Some were flung out of the solar system entirely, cast into interstellar space by close encounters with Jupiter. Others spiraled inward, pulled toward the Sun, where they eventually burned up or collided with the inner planets. Still others were captured by Jupiter itself, adding to the giant's mass, or becoming moons in orbit around it. What was left behind was a fraction of the original material, a sparse collection of rocks, too scattered and too perturbed to ever come together. This is why the asteroid belt has so little mass. Not because a planet was destroyed, but because most of the material that could have formed a planet was removed, ejected, scattered. The asteroid belt is what remains after Jupiter cleaned out the region, leaving only the leftovers, the fragments that happen to survive in stable orbits. But there's another layer to this story. Jupiter didn't just stir the asteroid belt through direct gravitational pulls. It also created what are called orbital resonances. A resonance occurs when two orbiting bodies have periods that are related by a simple ratio. For example, if one asteroid orbits the Sun twice, for every one time Jupiter orbits, they're in a 2-to-1 resonance. Every 2 orbits, the asteroid and Jupiter align in the same positions relative to the Sun. And each time they align, Jupiter's gravity gives the asteroid a small tug in the same direction. Over thousands or millions of orbits, these small tugs add up. They're like pushing someone on a swing. If you push at the right moment, matching the swing's natural rhythm, the swing goes higher and higher. In space, these resonant tugs can dramatically change an orbit, making it more elliptical, more tilted, or even ejecting the object entirely. And that's exactly what happened in the asteroid belt. Certain regions of the belt, at specific distances from the Sun, correspond to strong resonances with Jupiter. These regions are nearly empty today. We call them the Kirkwood gaps, named after the astronomer Daniel Kirkwood, who discovered them in 1866. If you plot the number of asteroids at different distances from the Sun, you see clear gaps at the resonant distances. 3-to-1 resonance, 5-to-2, 7-to-3. These are the places where Jupiter's influence is strongest, where any asteroid that wanders in gets its orbit destabilized and is eventually removed. The Kirkwood gaps are like invisible barriers carved by gravity. They shape the structure of the asteroid belt, dividing it into regions where asteroids can survive and regions where they cannot. And they're a direct signature of Jupiter's influence, a reminder that even though Jupiter is far away, its gravity reaches across millions of kilometers, sculpting the orbits of smaller bodies with invisible hands. Let that image rest in your mind for a moment. A giant planet orbiting slowly through space, and just by existing, just by being massive, it reshapes the region around it. It clears out zones. It creates gaps. It prevents worlds from forming. Jupiter didn't need to collide with anything. It didn't need to actively destroy a planet. Its gravity alone was enough to stop one from ever coming together. So the mystery of the missing planet is, in a way, a story about timing and location. If Jupiter had been smaller, or if it had formed later, or if it had been farther away, a planet might have formed between Mars and Jupiter. The material was there, the conditions were right, but Jupiter arrived first. It grew quickly, and by the time the inner solar system was taking shape, Jupiter's presence had already disrupted the region, scattering the building blocks before they could assemble. This is one of the key lessons of planetary formation. It's not just about having the right materials in the right place. It's also about what else is nearby, what other forces are at work. A solar system is a dynamic environment shaped by the interactions of many bodies, each one influencing the others through gravity. And sometimes those interactions prevent things from happening. They stop processes before they can complete. They leave behind gaps, silences, absences that tell a story of what might have been. As you rest tonight, consider this. The asteroid belt is not a failure. It's not a broken thing or a lost world. It's a consequence, a natural result of the way the solar system formed. It's what happens when a giant planet grows nearby, stirring the material that could have become a world, preventing it from gathering, leaving behind only scattered fragments. And those fragments, floating quietly in the space between Mars and Jupiter, are witnesses to that ancient process. They carry in their orbits, in their compositions, the memory of Jupiter's influence. Here's something to wonder about as you drift towards sleep. How different would the solar system be if Jupiter had never formed? Or if it had formed farther out, beyond Saturn, where its gravity couldn't reach the inner regions? Would there be a planet between Mars and Jupiter today? Would it be rocky like Mars, or icy like some of the outer moons? And if such a world existed, could it have been another home for life? Another blue-green world orbiting quietly in the sun's light? We'll never know. That timeline doesn't exist. But the question lingers, like a whisper in the dark. And it reminds us that the solar system we live in is just one possible outcome, shaped by chance and gravity and the order in which things happened. A different roll of the cosmic dice, and everything could have been different. Now that we understand Jupiter's role, we can look more closely at what actually exists in the asteroid belt. Because even though a planet never formed there, the belt is far from empty. It's home to hundreds of thousands of objects, each one unique, each one carrying clues about the early solar system. And among these countless rocks, there's one that stands out. One that's large enough, round enough, that it almost became something more. We call it Ceres. Ceres was the first asteroid ever discovered, remember? Giuseppe Piazzi found it on New Year's Day, 1801. For decades, astronomers called it a planet. Then, as more asteroids were found, it was reclassified. Just another asteroid, though the largest one. But in 2006, when the International Astronomical Union redefined what it means to be a planet, Ceres got a new designation. It became a dwarf planet. Not quite a full planet, but not just an asteroid either. Something in between. What makes Ceres special? Size, for one thing. It's about 940 kilometers across, roughly the size of Texas. That makes it by far the largest object in the asteroid belt. In fact, Ceres contains about 1/3 of the entire belt's mass. Everything else, hundreds of thousands of other asteroids, shares the remaining 2/3. Ceres is so large that its gravity pulled it into a round shape. Smaller asteroids are irregular, potato-shaped chunks of rock. But Ceres is spherical, or nearly so. It has layers, like a planet, a rocky core, a thick mantle, and possibly a thin crust. And here's what's remarkable. Ceres has water. Not liquid water on its surface, but water ice mixed into its interior, possibly even a subsurface ocean of briny liquid beneath the crust. When NASA's Dawn spacecraft visited Ceres between 2015 and 2018, it found bright spots on the surface, deposits of salt left behind by water that had seeped up from below and evaporated. It found evidence of cryovolcanism, ice volcanoes that erupt with salty water instead of molten rock. Ceres, this small world in the asteroid belt, shows signs of geological activity. It's not dead. It's not just a lifeless rock. It's a world with a history, with processes still at work beneath its surface. Think about that for a moment. Ceres could have been the core of a much larger planet. If Jupiter hadn't disrupted the region, if the material in the asteroid belt had been allowed to gather, Ceres might have grown. It might have pulled in more and more planetesimals, becoming larger, heavier, hot enough to melt and differentiate into distinct layers. It might have developed a thick atmosphere, retained heat from its formation, perhaps even supported conditions where liquid water could exist on its surface for a time. Instead, it remained small, a seed that never grew into a tree. And yet, Ceres survived. That's worth appreciating. Many objects in the asteroid belt were destroyed by collisions or ejected by Jupiter's gravity. But Ceres endured. It's been orbiting the Sun for over 4.5 billion years, holding its place in the belt, a quiet witness to the solar system's evolution. When you look at Ceres, you're looking at one of the oldest objects in the solar system, a remnant from the very beginning, unchanged in its essentials since the era of planet formation. The other large asteroids tell their own stories. Vesta, the second most massive object in the belt, is about 525 kilometers across. Unlike Ceres, Vesta is dry. It's made mostly of rock and metal, with a surface scarred by impacts. One of those impacts, sometime in the distant past, was so powerful it nearly destroyed Vesta entirely. It left a crater at the South Pole so deep you can see it from space, a vast basin surrounded by towering cliffs. The impact blasted fragments into space, creating the Vesta family of smaller asteroids that still orbit nearby. Vesta also has something unusual. It has a differentiated interior. That means it once got hot enough to melt, allowing heavy materials like iron to sink to the center and lighter materials to rise to the surface. This requires heat, a lot of it, more than you'd expect from such a small body. Where did that heat come from? Probably from radioactive decay. Elements like aluminum-26 that were present in the early solar system and generated heat as they decayed. Vesta might have been on its way to becoming a true planet, developing a core and mantle and crust before the material around it was scattered by Jupiter's influence. Then there's Pallas, the third largest, an irregular, heavily cratered world about 512 kilometers across. Pallas has one of the most tilted orbits in the belt, inclined at over 34 degrees to the plane of the solar system. That steep tilt means it's constantly crossing the paths of other asteroids, making it one of the most collision-prone objects in the belt. And yet, it has survived, battered and scarred, but intact. Each of these large asteroids is different. Ceres is icy and possibly active. Vesta is dry and differentiated. Pallas is tilted and heavily cratered. They don't fit a single pattern. They're not pieces of the same shattered world. They're individual objects, each with its own formation history, shaped by different conditions in different parts of the early solar nebula. And that diversity is one of the strongest pieces of evidence against the shattered planet theory. A single destroyed planet would have left behind fragments with similar compositions. But the asteroids are too varied. They formed separately, in different places, and were later gathered into the belt by the gravitational forces shaping the young solar system. Beyond the large asteroids, there are hundreds of thousands of smaller ones. Some are only a few kilometers across. Others are barely larger than boulders. Most are irregularly shaped, tumbling slowly through space as they orbit the Sun. Many have been battered by collisions, their surfaces covered in craters from impacts that happened millions or even billions of years ago. Some are loose rubble piles, collections of fragments held together by gravity rather than solid rock. If you stood on one of these rubble pile asteroids, you could jump high enough to escape its gravity entirely, drifting off into space like an astronaut on a spacewalk. The composition of asteroids varies widely depending on where they are in the belt. Asteroids closer to Mars tend to be rocky, made of silicate minerals similar to Earth's crust. These are called S-type asteroids. for silicaceous. Farther out, toward Jupiter, asteroids tend to be darker and richer in carbon. These are E-type asteroids, for carbonaceous. They're covered in organic compounds, the same kinds of carbon-based molecules that are the building blocks of life. And in the middle of the belt, you find the metallic asteroids, M-type, made mostly of iron and nickel. These might be the exposed cores of larger planetesimals that were shattered by collisions, their rocky mantles stripped away, leaving only the dense metal center. Can you picture the belt now? Not as a uniform cloud of rocks, but as a structured region, divided by composition, shaped by temperature gradients from the early solar nebula, organized by Jupiter's gravitational resonances. It's a layered system, a record of conditions in the early solar system, frozen in place. Each asteroid carries information about where it formed, what materials were available, how hot or cold the region was. And by studying them, by analyzing their compositions and orbits, scientists can reconstruct the history of the solar system's formation. There's something almost poetic about this. The asteroid belt, which seems at first like chaos, like random debris scattered through space, is actually highly organized. There are patterns, structures, families of asteroids that share similar orbits because they came from the same parent body. Gaps carved by resonances, zones where different types of asteroids dominate. It's not random at all. It's the result of billions of years of gravitational interactions, of collisions and resonances and slow orbital evolution. The belt has a story, written in the positions and motions of the rocks themselves. But here's something that might surprise you. The asteroid belt isn't static. It's still changing. Even now, collisions happen. Asteroids smash into each other at speeds of several kilometers per second, shattering into fragments, creating new smaller asteroids. Some of these fragments are knocked into orbits that bring them closer to the inner solar system, where they can cross Earth's path. We call them near-Earth asteroids, and there are thousands of them. Most are small, only a few meters or tens of meters across, but a few are large enough to be dangerous. This is how meteorites reach Earth. They're fragments of asteroids, knocked loose by collisions, slowly spiraling inward over millions of years until they encounter our planet. When they hit Earth's atmosphere, they burn up in a brilliant streak of light. We call them shooting stars, though they're not stars at all. They're pieces of the asteroid belt, visitors from the region between Mars and Jupiter, ending their long journey in a flash of heat and light. Some meteorites survive the fall. They hit the ground intact, and we can pick them up, study them, analyze their composition. These rocks are incredibly valuable to science. They're pieces of the early solar system, unchanged since the time of planet formation. By studying meteorites, we've learned about the temperature and pressure conditions in the solar nebula, about the timeline of planet formation, about the building blocks that came together to make the worlds we see today. Meteorites are messengers from the asteroid belt, carrying news from a time before Earth had oceans, before the moon existed, before life began. As you drift toward sleep, hold this thought gently. The asteroid belt is not just a curiosity. It's not just an interesting feature of the solar system. It's an archive, a library of ancient rocks, each one preserving information about the earliest days of our cosmic neighborhood. And even though no planet formed there, even though Jupiter's gravity prevented it, the belt itself has become something valuable, a resource, a window into the past, a collection of objects that tell us how planets form, how solar systems evolve, and what conditions were like in the disk of gas and dust that surrounded the young sun over 4.5 billion years ago. Here's a question to carry with you as you rest. If we could somehow remove Jupiter's influence, if we could gather all the asteroids together and let them merge, would they form a planet? Or has too much time passed? Has too much material been lost? The asteroid belt today contains only a fraction of what was once there. Most of the original material was ejected or scattered long ago. What remains might not be enough to build even a small planet. But it's interesting to imagine, isn't it? Taking those scattered fragments and bringing them together, watching them merge and grow, forming a new world in the space where one was meant to be. We've talked about how the asteroid belt formed, or rather, how it failed to form into a planet. We've looked at the largest objects, at Ceres and Vesta, and the countless smaller rocks scattered through the belt. But now, let's consider something else. What happens when asteroids leave the belt? When they wander into the inner solar system, crossing the orbits of the planets? Because this happens more often than you might think, and it has profound implications, not just for understanding the asteroid belt, but for understanding Earth's history, and perhaps even the origin of life itself. Not all asteroids stay in the belt. Some, through collisions or gravitational interactions, are nudged into different orbits. Their paths shift. They begin to cross the orbits of Mars, then Earth, then Venus. We call these near-Earth asteroids, and there are thousands of them out there right now, drifting through space on trajectories that bring them close to our planet. Most are small, harmless. They pass by without incident, separated from Earth by millions of kilometers. But occasionally, very occasionally, one of them hits. When an asteroid strikes Earth, the results can be catastrophic. The impact releases energy equivalent to thousands or even millions of nuclear bombs, depending on the size of the asteroid. The explosion creates a crater, throws debris high into the atmosphere, and can trigger fires, tsunamis, and climate changes that last for years. The most famous example is the impact that ended the age of dinosaurs. 66 million years ago, an asteroid about 10 kilometers across struck the Yucatan Peninsula in what is now Mexico. The impact created a crater 180 kilometers wide and triggered a mass extinction that wiped out about 75% of all species on Earth, including nearly all the non-avian dinosaurs. Think about that for a moment. A single rock from the asteroid belt, knocked loose by a collision or gravitational perturbation, drifted inward over millions of years. Its orbit gradually shifted until it crossed Earth's path. And then, on one particular day, 66 million years ago, Earth happened to be in the wrong place at the wrong time. The asteroid hit, and the world changed forever. The dominant life forms, creatures that had ruled the planet for over 160 million years, were gone within decades or centuries. And in the aftermath, in the world that slowly recovered from that impact, small mammals began to diversify and spread. Eventually, they gave rise to primates, and eventually, to us. So, in a strange way, we owe our existence to that asteroid. If it hadn't struck, if the dinosaurs had continued to thrive, mammals might have remained small and marginal, overshadowed by the great reptiles. The course of evolution would have been completely different. Humans, as we know ourselves, might never have existed. The asteroid that ended one era created the conditions for another. It's a reminder that catastrophe and opportunity are sometimes two sides of the same event. But impacts aren't only destructive. There's growing evidence that asteroids and comets might have delivered crucial materials to the early Earth. Water, for instance. Earth formed in the inner solar system, where temperatures were high enough that most water would have evaporated. So, where did Earth's oceans come from? One possibility is that they were delivered by impacts. Asteroids from the outer regions of the belt, the C-type asteroids rich in water ice, might have bombarded Earth during a period called the Late Heavy Bombardment, roughly 4 billion years ago. Each impact brought water, locked in the asteroid's ice, which melted and eventually filled the ocean basins. Asteroids might have brought more than water. They might have brought organic molecules as well. The carbonaceous asteroids contain complex organic compounds, the building blocks of life. Amino acids, nucleotides, sugars, all the chemical ingredients needed for biology. When these asteroids hit the early Earth, they delivered their cargo of organics, seeding the planet with the raw materials that would eventually lead to the origin of life. It's possible, even likely, that some of the molecules in your body right now originally came from an asteroid. Carbon atoms from the belt, delivered billions of years ago in a fiery impact, incorporated into the chemistry of life, passed down through countless generations, and ending up in you. Can you picture it? The asteroid belt, which seems so distant and irrelevant, might be intimately connected to our existence. It might be the source of the water we drink, the carbon in our cells, even the event that cleared the way for our evolution. The belt is not separate from Earth's story. It's part of it. A distant chapter, perhaps, but one that shaped everything that came after. This connection between Earth and the asteroids has made them scientifically invaluable. If we want to understand where we came from, where Earth's water originated, how life began, we need to study asteroids. And over the past few decades, we've begun to do exactly that. We've sent spacecraft to visit asteroids up close, to land on them, to analyze their surfaces, even to bring samples back to Earth. The first spacecraft to orbit an asteroid was near Shoemaker, which spent a year studying the asteroid Eros in 2000 and 2001. Eros is a near-Earth asteroid, a large S-type rock about 34 kilometers long. Near Shoemaker mapped its surface in detail, measured its composition, and even landed on it at the end of its mission, becoming the first spacecraft to touch down on an asteroid. The data it sent back revealed a world covered in craters and boulders, a surface shaped by billions of years of impacts, silent and ancient. Then came the Dawn mission, which we've already mentioned. Dawn visited two of the largest asteroids, Vesta and Ceres. Spending time in orbit around each one, it revealed Vesta's differentiated interior and massive South Pole crater. It discovered Ceres's bright salt deposits and possible subsurface ocean. Dawn showed us that even small worlds can be complex, with their own geology, their own histories. More recently, in 2018, Japan's Hayabusa 2 spacecraft arrived at an asteroid called Ryugu. Ryugu is a small, dark, carbon-rich asteroid, less than a kilometer across. Hayabusa 2 didn't just orbit it. It sent small rovers to hop across the surface, taking close-up images. It fired a projectile into the asteroid to create a fresh crater and study the material beneath the weathered surface. And then it collected samples, tiny grains of dust and rock from Ryugu's surface, and brought them back to Earth. Those samples arrived in December 2020, sealed in a capsule that survived re-entry and landed in the Australian desert. Scientists are still analyzing those grains, learning about Ryugu's composition, age, and history. NASA's OSIRIS-REx mission did something similar. It visited an asteroid called Bennu, another carbonaceous near-Earth asteroid about 500 meters across. OSIRIS-REx studied Bennu for 2 years, mapping every boulder and crater on its surface. Then, in October 2020, it performed a daring maneuver. It descended to the surface, extended a robotic arm, and touched Bennu for just a few seconds, blasting nitrogen gas to stir up dust and rocks. The arm collected a sample, several hundred grams of material from Bennu's surface. That sample returned to Earth in September 2023, and like Ryugu's samples, it's now being studied in laboratories around the world. Why go to all this trouble? Why spend billions of dollars and years of effort to collect a few grams of dust from an asteroid? Because those grains are pristine. They're unchanged since the solar system formed. Unlike meteorites, which burn and break apart as they fall through Earth's atmosphere, these samples were carefully collected in space and sealed away from contamination. They're as close as we can get to holding a piece of the early solar system in our hands. And what have we learned? We've learned that asteroids are more complex than we thought. Bennu's surface, for instance, is covered in boulders, far more than expected. There's hardly any fine dust or sand, just rocks. This tells us something about how asteroid surfaces evolve, how impacts and the harsh environment of space weather rocks over time. We've learned that some asteroids are rubble piles, held together loosely by gravity, rather than solid rocks. If you tried to land on one, your spacecraft might sink into the surface like stepping into gravel. We've also learned that asteroids are older than we can easily comprehend. The samples from Ryugu and Bennu contain grains that formed over 4.5 billion years ago, before the planets existed. Some of these grains might even be pre-solar, meaning they formed in other star systems and were incorporated into the cloud that became our solar system. When you look at these samples under a microscope, you're looking at material older than Earth, older than the Sun. You're looking at the dust from which worlds are made. Let that thought settle gently in your mind. The asteroid belt is not just a collection of rocks orbiting between Mars and Jupiter. It's a reservoir of ancient material, a time capsule preserving the conditions of the early solar system. Every asteroid is a fragment of that ancient time, carrying information that can't be found anywhere else. And by studying them, by visiting them, by bringing back samples, we're learning not just about asteroids, but about how planetary systems form, how life's building blocks are distributed through space, and how Earth became the living world we know today. As you rest tonight, consider this. The solar system is not a static place. It's dynamic, evolving, shaped by countless interactions over billions of years. The asteroid belt is part of that evolution. It's a region that was shaped by Jupiter, that failed to form a planet, but that still plays a role in the ongoing story of the solar system. Asteroids still collide. Fragments still drift inward. And occasionally, one of those fragments reaches Earth, connecting us to that distant belt, reminding us that we're part of a larger cosmic system, one that stretches from the Sun to the outer reaches of the solar system and beyond. Here's something to wonder about as you drift toward sleep. If we could travel to the asteroid belt, if we could stand on the surface of Ceres or Vesta and look up at the sky, what would we see? The Sun would be smaller, dimmer than it appears from Earth. Jupiter would dominate the sky, a bright disk far larger than any star. And scattered around you, if you looked carefully, you might see other asteroids, faint points of light drifting slowly through the dark. You'd be standing in a field of ancient rocks, witnesses to the solar system's birth, survivors of billions of years. Silent, patient, waiting. What do you think we'll find when we explore the asteroid belt more thoroughly? Could there be asteroids rich in metals, iron and nickel and platinum, that could one day be mined for resources? Could there be icy asteroids, hiding water that future space travelers could use? Or might there be something unexpected, something we haven't imagined yet, waiting to be discovered among those ancient rocks? Now let's explore something fascinating about the asteroid belt. Something that reveals just how interconnected these scattered rocks really are. Because even though the asteroids are spread across millions of kilometers, many of them are related. They're not all solitary wanderers. Some belong to families, groups of asteroids that share a common origin. And by studying these families, astronomers have learned to read the belt's history like detectives examining clues at a crime scene. An asteroid family forms when a larger asteroid is struck by another object with enough force to shatter it. The impact breaks the parent body into dozens, hundreds, or even thousands of fragments. These fragments fly apart, but they don't escape the solar system. They remain in orbit around the Sun, and because they all came from the same parent body, they share similar orbital characteristics. They move through space on paths that are close to each other, like siblings walking side by side. Over time, gravitational interactions slowly spread the fragments apart, but the family resemblance remains. Their orbits cluster together. Their compositions match. If you analyze their spectra, the light they reflect, you find the same minerals, the same chemical signatures. It's like finding shards of pottery scattered across a field and realizing they all came from the same broken vase. The first asteroid family was discovered in 1918 by a Japanese astronomer named Kyotsugu Hirayama. He noticed that certain groups of asteroids had very similar orbital elements, their semi-major axis, eccentricity, and inclination. The chances of this happening by accident, by random coincidence, were vanishingly small. The only explanation was that these asteroids shared a common origin. They were fragments of a larger body that had broken apart. Since then, astronomers have identified over 100 asteroid families. Some are large, with thousands of members. Others are small, just a handful of fragments. Each family tells a story A story of collision, of violence, of a moment when two objects met in space at speeds of several kilometers per second, and one or both of them shattered. Take the Coronis family, for example. It's located in the outer part of the main belt, and it contains over 300 known members, probably many more that haven't been discovered yet. All of them orbit the Sun at about the same distance, roughly 2.9 astronomical units. All of them have similar compositions, rocky S-type asteroids. And when you trace their orbits backward in time, when you use computer simulations to rewind their motions, they converge. They come together at a point in space, at a moment roughly 2.5 billion years ago. That's when the parent body broke apart. That's when the Coronis family was born. Can you picture it? 2.5 billion years ago. Long after the solar system had settled into its current configuration, long after the planets had formed and cleared their orbits, collision happened in the asteroid belt. A rock perhaps 90 kilometers across was struck by another asteroid. The impact shattered it, sending fragments flying in all directions. Those fragments are still out there, still orbiting, still carrying the memory of that ancient collision in their trajectories. Or consider the Vesta family, which we mentioned earlier. Vesta, one of the largest asteroids, has a massive crater at its south pole, carved by an impact so powerful it nearly destroyed the entire asteroid. The collision blasted thousands of fragments into space, and many of them are still orbiting near Vesta. We can identify them by their composition. They have the same spectral signature as Vesta's crust, a unique type of rock called eucrite. When meteorites with this same composition fall to Earth, we know where they came from. They're pieces of Vesta, knocked loose by that ancient impact, drifting through space for millions of years before eventually encountering our planet. This is one of the beautiful things about studying asteroids. We can connect them to meteorites. We can trace material from the belt all the way to Earth's surface. A meteorite lands in a field, or a desert, or on a frozen lake. Scientists analyze it, determine its composition and structure. Then they compare it to asteroid spectra, looking for a match. And sometimes they find one. They can say, with confidence, this rock came from that asteroid. It's a fragment of a specific world in the belt. And suddenly, that small rock in your hand becomes part of a larger story. A story that stretches across millions of kilometers and billions of years. But asteroid families don't just tell us about collisions. They also tell us about how asteroids age. When an asteroid breaks apart, fresh material is exposed. Material that hasn't been weathered by space. In space, there's no wind, no rain, no erosion in the way we understand it on Earth. But there is space weathering. Tiny micrometeorites constantly bombard asteroid surfaces, grinding them down grain by grain. Solar wind, a stream of charged particles from the sun, alters the surface chemistry. Cosmic rays, high-energy particles from distant supernovae, penetrate the rock and change its structure over time. These processes darken and redden asteroid surfaces, changing their appearance over millions of years. An asteroid that's been exposed to space for a long time looks different from one that's freshly broken. And when you look at asteroid families, you see this effect clearly. The youngest families have brighter, fresher-looking surfaces. The older ones are darker, more weathered. By studying how weathered an asteroid family is, astronomers can estimate how long ago the parent body broke apart. It's another piece of detective work, another way of reading the belt's history. There's something almost meditative about this. The idea that you can look at a rock drifting through space, measure the light it reflects, and determine not just what it's made of, but how long it's been exposed to the harsh environment of space. Time leaves its mark on everything, even on rocks floating in the vacuum between worlds. Nothing is unchanging. Everything ages, slowly, quietly, over timescales that dwarf human lifetimes. Let that thought settle in your mind. The asteroids we see today are not the same as they were when they formed. They've been shaped by billions of years of impacts, of space weathering, of gravitational interactions. They've collided and broken apart. They've drifted and evolved. The belt is not static. It's a living system, in a sense, constantly changing, constantly reshaping itself. And we're part of that process now. Human spacecraft have visited asteroids, landed on them, collected samples from them. We've even tested whether we can change an asteroid's orbit. In 2022, NASA's DART mission deliberately crashed a spacecraft into a small asteroid called Dimorphos, which orbits a larger asteroid named Didymos. The goal was to see if we could shift Dimorphos's orbit, to test whether this technique could be used in the future to deflect a dangerous asteroid heading toward Earth. The mission succeeded. The impact changed Dimorphos's orbital period by 33 minutes, more than expected. It was a proof of concept, a demonstration that if we needed to, if we detected an asteroid on a collision course with Earth decades in advance, we could potentially nudge it onto a safer path. Not by destroying it, which would just create many smaller dangerous fragments, but by gently pushing it, changing its trajectory by just enough that it misses Earth instead of hitting us. This is a new chapter in humanity's relationship with the asteroid belt. For all of history, we've been passive observers, watching the rocks drift by, occasionally getting hit when one crossed our path. Now, for the first time, we're becoming active participants. We're visiting asteroids. We're learning their secrets, and we're developing the capability to protect ourselves from impacts. Think about what that means. The asteroid belt, which formed billions of years ago, which failed to become a planet because of Jupiter's gravity, is now interacting with an intelligent species. A species that evolved on a small planet in the inner solar system, a planet that was itself shaped by asteroid impacts. And now that species is reaching outward, exploring the belt, learning from it, and beginning to exert its own influence on the trajectories of these ancient rocks. It's a strange loop, isn't it? Asteroids delivered the water and organics that made Earth habitable and possibly helped start life. An asteroid impact cleared the way for mammals to evolve, which eventually led to humans. And now humans are studying asteroids, visiting them, even changing their orbits. We're participants in the story now, not just subjects of it. As you rest tonight, let this image drift through your thoughts. A vast belt of rocks, scattered through space, each one carrying a history written in craters and composition. Some are solitary. Others belong to families, connected by ancient collisions. All of them are slowly evolving, aging under the constant bombardment of space, their surfaces gradually darkening over millions of years. And among them, occasionally, a small spacecraft appears, a visitor from the inner solar system, a representative of a species trying to understand where it came from and where it's going. Here's a gentle question to carry with you. When you look up at the night sky, knowing that the asteroid belt is out there, even though you can't see it with your naked eye, does it change how you think about the solar system? Does it feel more connected, more dynamic, knowing that material is constantly moving between the belt and the inner planets? That the rocks beneath your feet might contain atoms that once drifted in the belt? That the water you drink might have been delivered by an asteroid billions of years ago? The belt is not separate from us. It's part of the same system, part of the same story. And understanding that connection, feeling it, might be one of the most important things we can take away from this journey through the mystery of the missing planet. We've been focusing on the main asteroid belt, that wide band of rocks between Mars and Jupiter. But there's something else out there, something that reveals just how far Jupiter's gravitational influence reaches. Not all asteroids orbit in the belt. Some orbit much closer to Jupiter itself, trapped in stable regions where the giant planet's gravity and the sun's gravity balance perfectly. We call these the Trojan asteroids, and their existence opens a window into one of the most elegant aspects of orbital mechanics. Imagine you're holding two objects, one in each hand. Let's say one represents the Sun, the other represents Jupiter. Now imagine a third, much smaller object, an asteroid, trying to find a stable place to orbit in the system created by these two massive bodies. Most places are unstable. The gravitational pulls from the Sun and Jupiter combine in complicated ways, tugging the asteroid this way and that, eventually ejecting it or pulling it into one of the larger bodies. But there are 5 special points, 5 locations where the gravitational forces balance in just the right way that a small object placed there will stay there, at least for a very long time. These are called Lagrange points, named after the mathematician Joseph Louis Lagrange, who calculated their positions in the late 1700s. 3 of them lie along the line connecting the Sun and Jupiter. 1 sits between them. 1 sits beyond Jupiter. 1 sits beyond the Sun on the opposite side from Jupiter. These 3 are unstable. If you nudge an object away from them even slightly, it drifts away and doesn't come back. But the other 2 Lagrange points are different. They're stable, or at least semi-stable. They form equilateral triangles with the Sun and Jupiter. One sits 60 degrees ahead of Jupiter in its orbit. The other sits 60 degrees behind. If you placed an asteroid at either of these points and gave it a gentle push, it wouldn't drift away. It would oscillate around the point, tracing a slow loop, but remaining near the Lagrange point indefinitely. These are called the L4 and L5 points. And they're not empty. They're filled with asteroids. The first Trojan asteroid was discovered in 1906 by the German astronomer Max Wolf. He named it Achilles, after the Greek hero from the Trojan War. As more were discovered, astronomers continued the tradition, naming asteroids at Jupiter's L4 point after Greek heroes and those at the L5 point after Trojan heroes. It's a playful reminder of the ancient war, with Greeks and Trojans forever frozen in their positions, separated by Jupiter, never able to reach each other. Today, we know of over 10,000 Jupiter Trojans, though there are likely millions more too small or too faint to detect. They form 2 distinct clouds, one ahead of Jupiter, one behind, each occupying a region of space roughly as large as Jupiter's orbit itself, and they're old. These asteroids have been trapped at the Lagrange points for billions of years, possibly since the solar system formed. They're survivors from the earliest era, held in place by the elegant balance of gravity. Think about that for a moment. While the asteroids in the main belt were being scattered and stirred by Jupiter's gravity, while planetesimals were colliding and breaking apart, the Trojans were safe, protected. They found refuge at the Lagrange points, where the forces balanced perfectly, and they've remained there ever since. They're like fossils, preserving conditions from the very beginning, untouched by the chaos that shaped the rest of the belt. And Jupiter isn't the only planet with Trojans. Mars has a few. Neptune has many, possibly even more than Jupiter. Earth has at least one confirmed Trojan asteroid, a small rock about 300 meters across that orbits at Earth's L4 point. It was discovered only in 2010, which tells you how difficult these objects are to find. They're faint, and from Earth's perspective, they're always close to the Sun in the sky, making them hard to observe. The existence of Trojans tells us something profound about how solar systems work. Lagrange points aren't just mathematical curiosities. They're real places where objects accumulate. And if our solar system has them, then other solar systems probably do too. Every planet with a significant mass creates Lagrange points with its star. And if those points can trap asteroids, they might trap other things as well. Dust, gas, maybe even small moons or planets in some systems. Can you picture it? Not just one belt of asteroids, but multiple populations. The main belt between Mars and Jupiter, the Trojans ahead of and behind Jupiter, the near-Earth asteroids crossing the inner solar system, the distant asteroids beyond Neptune in the region we call the Kuiper Belt. All of them are part of the same story, remnants from the solar system's formation, sorted into different regions by gravity and orbital dynamics. And here's where things get even more interesting. The asteroid belt isn't uniform. Even within the main belt, there are structures, regions where asteroids are more common, and regions where they're rare. We've already talked about the Kirkwood gaps, the empty zones created by resonances with Jupiter. But there are other features too. The belt is divided into 3 main regions. The inner belt, from about 2.1 to 2.5 astronomical units. The middle belt, from 2.5 to 2.8. And the outer belt, from 2.8 to 3.3 astronomical units. Each region has a different character. The inner belt is dominated by S-type asteroids, rocky and relatively bright. The middle belt has a mix of types. The outer belt is rich in C-type asteroids, dark and carbonaceous, remnants from the colder regions of the early solar nebula. This layering tells us about temperature gradients in the early solar system. It shows us where water could condense, where rocky materials dominated, where organic compounds remained stable. The belt is like a cross-section of the solar nebula, frozen in time. And within these regions, there are smaller structures, clusters of asteroids with similar compositions, streams of fragments from ancient collisions, zones where asteroids are tilted or eccentric, their orbits perturbed by gravitational interactions. The belt is not a simple disk of uniform debris. It's complex, layered, full of patterns that reflect billions of years of evolution. Let that complexity sink in for a moment. Every asteroid in the belt has a story: where it formed, how it survived, what collisions it experienced, how its orbit changed over time. And all of these individual stories combine to create the larger story of the belt itself. It's like looking at a forest and seeing not just trees, but the history of fires and storms and seasons that shaped each tree's growth. The belt is alive with history, even though the rocks themselves are silent and cold. As you rest tonight, consider this. The solar system is not a collection of isolated objects. It's a web of interactions, of gravitational influences, of exchanges of material and energy. The asteroid belt connects to Jupiter through resonances and perturbations. It connects to Earth through meteorite deliveries and occasional impacts. It connects to the outer solar system through objects that drift between regions. Everything is linked. Everything influences everything else, over timescales that stretch across billions of years. And we're just beginning to understand these connections, just beginning to map the belt in detail, to identify families, to trace the history of collisions and migrations. Every new observation, every spacecraft mission, every meteorite analysis adds another piece to the puzzle. Slowly, patiently, we're learning to read the story written in the positions and compositions of the asteroids. Here's something to wonder about as you drift toward sleep. What would it be like to live in the asteroid belt? Not on a single asteroid, but moving between them, perhaps in a future where humanity has spread beyond Earth and begun to explore the belt directly. You'd travel in a spacecraft, drifting from rock to rock, each one a different world. Some would be large enough to have noticeable gravity, where you could walk on the surface, feeling the gentle tug holding you down. Others would be so small you'd float above them, tethered by a line to prevent drifting away. The sun would be dimmer than it is from Earth, about a third as bright, but still the dominant light in the sky. Jupiter would be visible, a bright disk, sometimes ahead of you, sometimes behind, depending on where you were in the belt. And if you looked carefully, you might see other asteroids, faint points of light drifting through the dark, fellow travelers in the belt's slow orbit around the sun. It would be quiet. No sound, of course. Space is a vacuum. But even visually, the belt would feel empty. The asteroids are so far apart that you'd rarely see more than one or two at a time. Most of the time, you'd be surrounded by darkness and stars, with only the faint sunlight and distant Jupiter to orient yourself. And yet, you'd know you were in a special place. A place where a planet should have formed, but didn't. A place filled with ancient rocks, each one a time capsule from the solar system's birth. A place that connects to Earth's history, that shaped the evolution of life, that might one day provide resources for future generations. The belt would feel both empty and full of significance, a quiet archive drifting through space. Do you think humans will ever live in the asteroid belt? Will we build stations there, mine the asteroids for metals and water, create new habitats among the rocks? Or will the belt remain as it is, a distant region visited only by robotic probes and studied from afar? It's hard to know, but it's interesting to imagine, isn't it? A future where the belt is not just an object of study, but a frontier. A place where people work and explore and build, bringing life and activity to a region that's been silent for billions of years. Now let's turn our attention to something that might surprise you. For all we've learned about the asteroid belt, for all the observations and spacecraft missions and computer simulations, there are still mysteries. Questions we can't fully answer. Things that don't quite fit our current understanding. And sometimes, these mysteries are the most interesting part of the story because they remind us that science is not finished, that there's always more to discover. One of the biggest puzzles is this: where did all the water go? When you look at the composition of asteroids, especially the outer ones, you find evidence that many of them contain water ice, or at least they did at some point in their history. Some of the carbonaceous asteroids still have water locked inside, mixed with minerals or trapped in their structures. And yet, the amount of water in the asteroid belt today is far less than you'd expect based on where it formed. Remember, the outer part of the belt sits beyond the frost line, the boundary where temperatures in the early solar nebula were cold enough for water to freeze. Beyond this line, water ice was abundant. It's why the outer planets grew so large, why Jupiter and Saturn have such massive atmospheres. There was simply more material available. Ice is common in the universe. Water, that simple molecule made of 2 hydrogen atoms and 1 oxygen atom, forms easily wherever temperatures are low enough. So the outer asteroid belt should be rich in water, and yet it isn't. Most of the asteroids there are relatively dry. Where did the water go? Was it lost through impacts, vaporized when asteroids collided at high speeds? Was it pulled away by Jupiter's gravity, along with most of the other material in the belt? Or was it delivered to the inner solar system, to Earth and the other rocky planets, during the heavy bombardment period? This is one of those questions where we have partial answers, but not complete ones. We know water was delivered to Earth somehow. We know asteroids contain organic compounds and water ice. We know the belt was once more massive than it is today. But connecting all these pieces into a complete story is difficult. There are gaps, uncertainties, places where the evidence points in multiple directions. Think about this gently. The universe doesn't always give us neat, simple answers. Sometimes the truth is complicated, messy, shaped by many overlapping processes that happened over millions of years. The asteroid belt story involves collisions, gravitational scattering, thermal evolution, chemical reactions, and orbital migrations. Each of these processes left its mark. Untangling them, figuring out which effects were caused by which processes, requires careful detective work. And here's another mystery. Some asteroids are active. They show tails, like comets, even though they orbit in the asteroid belt where ice shouldn't sublimate easily. We call them main belt comets or active asteroids. The first one was discovered in 1996, an asteroid called Elst-Pizarro that developed a faint tail. Since then, we've found about 24 more. What causes these tails? On comets, tails form when ice on the surface sublimates, turns from solid directly to gas, carrying dust particles with it. But asteroids in the belt are too far from the sun for surface ice to sublimate normally. So something else must be happening. Maybe there's ice just beneath the surface, exposed by a recent impact. Maybe the asteroid's rotation brings subsurface ice into sunlight at certain angles. Or maybe it's not sublimation at all. Maybe the tail is caused by impacts, dust kicked up by micrometeorite collisions, or by the asteroid breaking apart slowly. Each explanation has problems. Each leaves questions unanswered. And that's okay. That's actually what makes science exciting. Not the questions we've answered, but the ones we're still working on. The mysteries that keep us curious, that drive us to build better telescopes, send more spacecraft, develop new techniques for analysis. Can you picture scientists studying these active asteroids, watching them develop tails, trying to figure out what's happening? It's like being a detective examining a crime scene, except the crime scene is millions of kilometers away, moving through space, and you can only observe it with telescopes and spacecraft. You gather evidence, you develop theories, you test them, and slowly, piece by piece, the picture becomes clearer. There's also the question of how the asteroid belt structure evolved over time. We know Jupiter's gravity shaped the belt. We know collisions broke larger bodies into smaller fragments. But the details are still being worked out. Computer simulations can recreate some aspects of the belt's history, but they depend on assumptions about the initial conditions, about how much mass was originally in the belt, about how quickly Jupiter formed, about the timing of orbital migrations. One of the most intriguing ideas to emerge in recent decades is called the Grand Tack hypothesis. It suggests that Jupiter didn't form where it is now. Instead, it formed farther out and then migrated inward, moving toward the sun like a ship tacking against the wind. As it moved inward, it scattered material, clearing out much of the inner solar system. Then, once Saturn formed and caught up with Jupiter, the two giants became locked in an orbital resonance that reversed their migration. They moved outward again, settling into the orbits we see today. If this happened, it would explain a lot. Why the asteroid belt has so little mass. Why Mars is so small compared to Earth. Why certain types of meteorites seem to have formed in the inner solar system but are now found in the outer belt. Jupiter's migration would have stirred everything, mixing material from different regions, scattering planetesimals, reshaping the entire solar system. But did it actually happen? The evidence is suggestive but not conclusive. Some observations fit the Grand Tack model beautifully. Others don't quite match. It's an active area of research, with scientists debating the details, running new simulations, looking for new evidence that could confirm or refute the idea. And this brings us to something important. The asteroid belt isn't just interesting because of what it tells us about our solar system. It's interesting because it tells us about planetary formation in general. How do planets form? What conditions are necessary? What can prevent them from forming? These are universal questions. Every star that has planets went through some version of the process our solar system went through. By understanding our asteroid belt, we learn about what might be happening around other stars. In recent years, we've discovered thousands of exoplanets, planets orbiting other stars. Some of these systems look nothing like ours. Hot Jupiters, massive planets orbiting extremely close to their stars, completing an orbit in just a few days. Super-Earths, rocky planets larger than Earth but smaller than Neptune, a type we don't have in our solar system. Systems where multiple planets orbit in tight, compact configurations, all closer to their star than Mercury is to our Sun. These discoveries have challenged our understanding of planetary formation. We thought our solar system was typical, but it turns out it might be unusual in some ways. And one of those ways is the asteroid belt. Not many other systems show clear evidence of an asteroid belt like ours. Maybe they have them, but we just can't detect them yet. Our telescopes aren't sensitive enough to see small rocks around distant stars. Or maybe belts like ours are actually rare. Maybe in most systems, the material between the inner rocky planets and the outer giants either forms a planet or gets scattered away completely, leaving nothing behind. If our belt is unusual, that raises interesting questions. Why do we have one? What specific sequence of events preserved it? And does the presence of a belt affect the evolution of the system? Does it deliver material to the inner planets that wouldn't otherwise reach them? Does it affect the long-term stability of the planetary orbits? These are questions we're only beginning to explore. As our telescopes improve, as we discover more exoplanetary systems and study them in greater detail, we'll learn more about how common or rare asteroid belts are. And that will feed back into our understanding of our own belt, helping us see it in a broader context. Let that thought rest gently in your mind. The asteroid belt, that gap between Mars and Jupiter, that collection of scattered rocks that failed to become a planet, might be a key to understanding planetary systems throughout the galaxy. By studying the rocks in our own backyard, we learn about processes happening light years away, around stars we'll never visit, shaping worlds we'll never see. As you drift toward sleep, consider this. Every mystery we solve reveals new mysteries beneath it. We thought we understood the asteroid belt, that it was simply the remains of a shattered planet. Then we learned that wasn't true. We thought Jupiter's gravity explained everything, but then we discovered active asteroids and had to rethink our assumptions. We thought the belt was static, but now we know it's dynamic, still evolving, still shaped by collisions and resonances and the slow migration of fragments. Science is not about reaching final answers. It's about asking better questions, about looking more carefully, about being willing to revise our understanding when new evidence appears. And the asteroid belt, humble as it may seem, is teaching us these lessons. It's showing us that even a failed planet, even a collection of scattered rubble, has a story worth understanding. Here's a thought to carry with you. What other mysteries might be hiding in the asteroid belt? What haven't we discovered yet because we haven't looked in the right place or asked the right question? Could there be asteroids with unusual compositions that would tell us something new about the early solar system? Could there be structures we haven't noticed? Patterns in the orbits that would reveal new aspects of how the belt evolved? What will the next generation of telescopes and spacecraft find when they turn their attention to these ancient rocks? The belt has been orbiting the Sun for over 4.5 billion years. It will continue orbiting for billions more. We've been studying it seriously for only a few decades. There's so much left to learn, so many questions still waiting for answers. And that's not a problem. That's an invitation. An invitation to keep exploring, keep questioning, keep seeking to understand this remarkable collection of rocks drifting silently between the worlds. As we near the end of our journey through the asteroid belt, let's look ahead. Not just at what we've learned, but at what the belt might mean for humanity's future. Because the asteroid belt isn't just a chapter in the solar system's past. It might also be a chapter in our future, a resource, a destination, a stepping stone to the outer reaches of the solar system and beyond. For now, the belt remains largely unexplored. We visited only a handful of asteroids up close, a few flybys, a few orbits, a couple of sample return missions. Out of the millions of objects in the belt, we've studied perhaps a dozen in detail. It's like having a vast library and reading only a few pages from a few books. There's so much more waiting to be discovered. But that's changing. Plans are being developed for new missions. NASA, ESA, JAXA, and other space agencies around the world are looking at asteroids with renewed interest. Not just for scientific reasons, though those remain important, but for practical ones as well. Because asteroids contain resources, metals, water, minerals, materials that could be valuable, not just on Earth, but in space. Think about what it takes to launch something from Earth into space. You need enormous rockets burning vast amounts of fuel just to escape our planet's gravity. Every kilogram costs thousands of dollars to lift into orbit. It's expensive, difficult, limited by the strength of our rockets and the amount of fuel they can carry. But asteroids are already in space. They have almost no gravity. You could land on one with a tiny spacecraft, extract materials, and use them without ever having to lift them out of a gravity well. Water, for instance. If you could mine water ice from an asteroid, you could split it into hydrogen and oxygen. Hydrogen and oxygen, when burned together, make rocket fuel. So an asteroid with water becomes a refueling station, a place where spacecraft traveling through the solar system could stop, refill their tanks, and continue their journey. You wouldn't need to carry all your fuel from Earth. You could gather it along the way. Metals are even more interesting. Some asteroids are almost pure iron and nickel. A single metallic asteroid just a few hundred meters across could contain more platinum group metals than have ever been mined on Earth. These are rare elements used in electronics, catalysts, and various industrial processes. On Earth, they're expensive because they're scarce. But in the asteroid belt, they're common. Entire worlds made of the stuff. Could we mine them? Could we extract these materials and bring them back to Earth or use them to build structures in space? The idea has been around for decades. It's called asteroid mining. And while it remains mostly theoretical, mostly the domain of science fiction and enthusiastic entrepreneurs, the basic physics is sound. There's no fundamental reason it couldn't work. It's just a matter of developing the technology, making it economical, figuring out the logistics, Some companies have already started exploring the idea. They've studied which asteroids would be easiest to reach, which ones contain the most valuable materials, what techniques could be used to extract and process resources in the zero-gravity, vacuum environment of space. None of them have actually mined an asteroid yet. But the groundwork is being laid. The first serious attempts might happen within your lifetime. Can you picture it? Robotic spacecraft landing on asteroids, drilling into their surfaces, extracting water or metals, processing them on site, and either shipping them back to Earth or using them to build habitats and fuel depots in space. The asteroid belt could become a resource hub, a place where materials are gathered and processed, supporting humanity's expansion beyond Earth. And it's not just about materials. The asteroid belt could also serve as a destination in its own right, a place to explore, to study, to live. Imagine small research stations built on the largest asteroids, on Ceres or Vesta, where scientists could study the rocks up close, drill deep beneath the surface, analyze compositions in laboratories, search for organic compounds and water. These stations could be stepping stones, places where travelers heading to Jupiter or Saturn or beyond could stop, rest, resupply. The journey to the outer solar system is long. It takes years to reach Jupiter, even longer to reach Saturn or Neptune. But if there were stations in the asteroid belt, halfway between Earth and Jupiter, the journey could be broken into stages. Launch from Earth, travel to the belt, rest and refuel, then continue outward. It would make the outer solar system more accessible, less of a distant frontier, and more of a connected network. Of course, all of this depends on whether we choose to pursue it, whether we invest in the technology, develop the capabilities, commit to exploring and utilizing the resources of the belt. It's not inevitable. It's a choice that future generations will make based on their priorities, their needs, their sense of curiosity and adventure. But here's what's remarkable. The possibility exists. The asteroid belt, which formed billions of years ago when a planet failed to come together, might someday become a resource that enables humanity to spread beyond Earth. A failed planet might become the key to humanity's expansion into the solar system. There's something poetic about that, something fitting. Let that thought drift through your mind gently. The belt has already shaped Earth's history. It delivered water and organics that made life possible. It sent the impact that ended the dinosaurs' reign and opened the way for mammals. And now, looking forward, it might shape humanity's future, providing resources and destinations as we take our first steps beyond our home planet. And there's another aspect to consider. The asteroid belt is a scientific treasure. Every rock in the belt is a piece of the early solar system, preserved for billions of years. By studying them, we learn not just about asteroids, but about how planetary systems form, how chemistry evolved in the early solar nebula, what conditions were like when the sun was young. The belt is a time capsule, a library of ancient history written in stone. As our technology improves, we'll be able to study the belt in greater detail. Future telescopes will catalog more asteroids, measure their compositions more precisely, track their orbits with greater accuracy. Spacecraft will visit more of them, perhaps dozens or hundreds over the coming decades. Each mission will add to our understanding, revealing new details, answering old questions, raising new ones. And maybe someday, we'll answer the question that started this journey. Why is there no planet between Mars and Jupiter? We have a good answer now. Jupiter's gravity prevented one from forming, but the details are still being worked out. How much mass was originally there? How quickly was it scattered? What role did orbital migrations play? How much material was delivered to the inner planets? How much was ejected into interstellar space? These questions might seem abstract, disconnected from daily life. But they're part of understanding our place in the universe, understanding where we came from, how the solar system formed, what forces shape the world we live on. And in a deeper sense, they're about understanding process itself, how complex systems evolve, how chance and necessity interact, how something as simple as gravity, acting over millions of years, can shape the structure of an entire planetary system. As you rest tonight, let these thoughts settle gently. The asteroid belt is not just a gap in the solar system. It's not just a collection of rocks. It's a story about formation and disruption, about what happens when forces prevent something from coming together, about how the pieces that remain tell us about what might have been. And it's a story that connects past and future, linking the early solar system to Earth's history and possibly to humanity's future among the stars. Here's a question to carry softly into sleep. If you could visit one asteroid, any asteroid in the belt, which would you choose? Would it be Ceres, the largest, with its mysterious bright spots and possible subsurface ocean? Would it be Vesta, with its massive crater and differentiated interior? Would it be one of the smaller ones, an irregular tumbling rock covered in craters, a fragment of something larger that broke apart long ago? Each one has its own character, its own story. Each one offers a different perspective on the belt's history. Or maybe you'd want to visit one of the Trojans, those asteroids trapped at Jupiter's Lagrange points, stable and ancient, following the giant planet in its orbit like faithful companions. From there, you'd see Jupiter dominating the sky, far larger than any moon or planet we see from Earth. You'd be at the edge of the inner solar system, looking outward toward the giants, standing in a place where gravity balances perfectly, where an asteroid can rest for billions of years without drifting away. Wherever you chose to visit, you'd be standing on history, on a piece of the early solar system that has survived unchanged for over 4 billion years. You'd be touching the building blocks of planets, the same materials that came together to make Earth and Mars and all the rocky worlds. And you'd be part of the continuing story, adding a new chapter where humans reach out beyond their home planet to explore the ancient rocks drifting in the space between worlds. And so we come to the end of our journey. A journey that began with a simple question: why is there no planet between Mars and Jupiter? We've traveled through billions of years of history, from the solar nebula's collapse to the present day. We've explored the forces that shaped the asteroid belt, the rocks that survived, and the mysteries that remain. And now, as you rest, let's bring it all together. Let's see the full picture, the complete story of the missing planet that never was. The asteroid belt exists because of timing, because of location, because of Jupiter. When the solar system was young, when planets were forming from the disk of gas and dust around the sun, the region between Mars and Jupiter should have produced a world. The materials were there, the conditions were right. Planetesimals began to gather, just as they did everywhere else in the solar system. But Jupiter formed quickly. It grew massive, and its gravity reached into that region, stirring the planetesimals, increasing their velocities, making collisions destructive rather than constructive. Over millions of years, most of the material was scattered. Some was pulled into Jupiter. Some was flung into the outer solar system or beyond. Some spiraled inward, eventually colliding with the inner planets or falling into the sun. What remained was a fraction of what had been there, a sparse collection of rocks, too scattered and too perturbed to ever come together into a single world. And so the asteroid belt is not the grave of a destroyed planet. It's the nursery of a planet that never grew up, a collection of building blocks that were never assembled. And those building blocks, those scattered fragments, have been orbiting the sun for over 4.5 billion years. Silent witnesses to the solar system's history. Think about everything those rocks have seen. They were there when Earth formed, when the moon was created by a massive impact, when the late heavy bombardment sent waves of asteroids crashing into the inner planets. They were there when life began on Earth, when the first cells divided, when photosynthesis filled the atmosphere with oxygen. They were there when complex life emerged, when animals first crawled onto land, when dinosaurs ruled and then vanished. They were there through it all, orbiting quietly, unchanged, patient. And they're still there now, still orbiting, still carrying their ancient story. Every crater on their surfaces is a record of a collision. Every mineral in their structures tells us about the temperature and pressure where they formed. Every orbit reveals the gravitational forces that shape them. The asteroids are books, a vast library drifting through space, and we're learning to read them. What have we learned? We've learned that planetary formation is not always smooth, that disruption is part of the process, that not every region of a solar system produces a planet. We've learned that gravity is subtle and powerful, capable of preventing formation without destroying anything directly. We've learned that the solar system is dynamic, shaped by migrations and resonances and interactions between bodies over billions of years. We've also learned humility. The asteroid belt reminds us that we don't have all the answers yet. There are still mysteries, active asteroids we can't fully explain, water that seems to have disappeared, details about the belt's evolution that remain uncertain, and that's okay. That's how science works. We gather evidence, develop theories, test them, revise them when new information appears. The process never ends. There's always more to discover. Can you feel it? The way understanding changes how you see things? When you look up at the night sky now, you might not be able to see the asteroid belt with your naked eye. It's too faint, too scattered, but you know it's there. You know those millions of rocks are orbiting between Mars and Jupiter, carrying their ancient stories, shaped by forces that span billions of years. And that knowledge connects you to it, makes you part of the story in a way you weren't before. Because here's the thing, you are connected to the asteroid belt. The atoms in your body, the carbon and oxygen and iron and calcium, were forged in stars that died long before the solar system formed. Those atoms drifted through space, became part of the solar nebula, condensed into rocks and ice and gas. Some became the sun, some became Jupiter, some became asteroids, and some eventually made their way to Earth, were incorporated into living things, passed down through generations, and ended up in you. The iron in your blood might have once been part of an asteroid. The water you drink might have been delivered by an impact billions of years ago. The calcium in your bones, the oxygen you breathe, all of it traces back to the same ancient materials that formed the asteroid belt. You're made of the same stuff. You're part of the same story. And that story is still being written. Spacecraft are visiting asteroids, collecting samples, analyzing their compositions. Telescopes are discovering new ones, tracking their orbits, measuring their properties. Scientists are developing theories, running simulations, trying to understand the details of how the belt formed and evolved. And maybe someday, humans will travel to the belt themselves, standing on those ancient rocks, looking up at Jupiter, experiencing directly what we've only been able to study from afar. The future is uncertain. We don't know how much of this will happen. We don't know if asteroid mining will become a reality, if the belt will become a resource hub, if humans will build stations among the rocks. But the possibility exists, and that's worth something. The asteroid belt, which formed because a planet failed to come together, might become a key to humanity's expansion beyond Earth. A failed planet becoming a stepping stone to the stars. Let that thought rest gently in your mind. There's something beautiful about it, something that speaks to resilience, to finding value in unexpected places, to understanding that failure in one context can be opportunity in another. The asteroid belt is not a mistake. It's not a broken thing. It's what it is, shaped by the forces that acted on it, carrying its history forward, still part of the solar system's ongoing story. As you drift into sleep, let these images fade softly. The scattered rocks orbiting in the dark. Jupiter's massive presence, subtle and powerful, shaping orbits across millions of kilometers. The ancient collisions that broke asteroids apart, creating families that still move together. The slow weathering of surfaces over billions of years. The occasional fragment that spirals inward, eventually falling to Earth as a meteorite, connecting the belt to our world. And somewhere in that vast collection of rocks, Ceres drifts along, the largest of them all, round and ancient, possibly hiding an ocean beneath its icy crust. Nearby, Vesta tumbles through space, scarred by the impact that nearly destroyed it. And scattered around them, millions of smaller asteroids, each one unique, each one carrying its piece of the story. The mystery of the missing planet is solved, or at least mostly solved. We know there was never a planet that shattered. We know Jupiter's gravity prevented one from forming. We understand the mechanisms, the resonances, the scattering processes. But the asteroid belt itself remains full of smaller mysteries, questions that keep scientists curious, details that haven't been worked out yet. And maybe that's the most important lesson. That understanding is not a destination, but a journey. That every answer reveals new questions. That the universe is deeper and more complex than we can fully grasp. But we can keep learning, keep exploring, keep pushing the boundaries of what we know. You've traveled far tonight, from the inner solar system to the belt and beyond. From the present back to the solar system's formation 4.5 billion years ago. From scattered fragments to the story of how planets form. You've seen how gravity shapes worlds, how timing matters, how chance and necessity interact to create the universe we observe. And now it's time to rest. The asteroids will keep orbiting. Jupiter will continue its slow circuit around the sun. The belt will remain, patient and ancient, waiting for the next spacecraft, the next discovery, the next chapter in its ongoing story. But for now, you've learned enough. You've traveled enough. You can let it all settle, let the thoughts drift away, let sleep carry you gently into the dark. Thank you for joining me on this journey through the mystery of the missing planet. If these quiet explorations help you unwind or give you something to think about as you rest, you might consider subscribing to the channel or leaving a gentle like. It helps others find their way here too. One sleepy soul at a time. The asteroid belt is out there, orbiting between Mars and Jupiter, a collection of ancient rocks that failed to become a planet. And yet, in failing to become one thing, it became something else, something valuable, something that connects Earth's past to its possible future, something that reminds us that even in emptiness, even in absence, there's a story worth understanding. Sleep well tonight, knowing that you're part of that story, that the universe is vast and ancient, but also connected in ways that span from the smallest atom to the largest galaxy. You're made of stardust. You're shaped by forces that stretch back billions of years. And somewhere out there, in the space between worlds, millions of rocks drift silently through the dark, carrying their ancient memories, waiting patiently for us to understand. Good night, and may your dreams be filled with quiet wonders from the space between the worlds.